This chapter deals with reactions of alcohols, and so far we've talked about elimination reactions of alcohols. We've also introduced a new concept of carbocation rearrangements, and now we're transitioning into talking about substitution reactions of alcohols. So thinking back to our two rules of organic chemistry, negatives flow to positives, and we go from high energy to low energy species, so the ball rolling downhill. What do you expect this reaction to proceed in the forward direction as I've written it? So in the course packet, I have this outlined as kind of a clicker question. There's which side is favored, reactants, products, both sides are equal, or you're guessing. So pause real quick and think about which side you think would be more stable here. Okay, you've thought about it, you've written something down, and you're back. So essentially what we're really comparing is the stability of ions. On this side of the reaction we have sodium plus and sodium plus. That's going to be basically the same stability. It's the same type of ion. But on this side we have a bromide, Br minus, and we have OH minus on the product side. So what's more stable, Br minus or OH minus? So hopefully that gets you thinking back to pKa's, right? HBr is a super strong acid. It's stronger than HCl. HCl is a pKa of -7. So that tells us that this is going to be if we're a strong acid, we have a really stable, weak conjugate base. This is a really weak, stable conjugate base. The conjugate acid of OH minus would be water. Its pKa would be about 16. This is much more reactive. So this wouldn't go in the forward direction. This would be fully in the reverse direction. And why is that? That's because Br minus is more stable than OH minus. So the reaction is unfavorable. And we already kind of saw this. We saw this in the elimination reactions, right? We said it's easy to eliminate a halogen because it's really stable by itself. It's a really good leaving group. OH minus is not a good leaving group. So what did we do in those elimination reactions to make the OH into a good leaving group? We protonated it with a strong acid like sulfuric acid. Turns out that things are going to be a little bit different when we use acids such as HBr, HCl, etc. More on that in a moment. All right, we're back. So when we treat, alcohols, not a good leaving group by themselves. How did we make them into a good leaving group with elimination? We protonated them with sulfuric acid. What if we have a different acid like HBr? HBr is actually even a stronger acid than sulfuric acid. So it's going to result in the same type of chemistry, right? The OH is a moderate base, moderate nucleophile. But if we have a super strong acid that really wants to give up that proton, this is going to lead to an acid-base reaction where we would generate OH2, which is our good leaving group, plus Br minus. So reacting an alcohol with HX, we're not going to say HBr specifically because the X could be Br, it could be chlorine, could be iodine. So reacting ROH with HX transforms the alcohol into a good leaving group. So we have our really good leaving group. Do we have a strong nucleophile? No, we don't, right? This is a really strong acid, so that tells us that this is a weak nucleophile, a weak base, and that's going to result in unimolecular type chemistry if it's possible. So this is a secondary leaving group. It can form a carbocation, so that's what's going to happen. This is going to ionize to the carbocation. And what else do we have in solution? So we have a few things, right? We have water. We just got that from that leaving. We have Br minus. And we also have more HBr. So there's an excess of this around. So what's going to happen here? Well, what's the stronger nucleophile base over these two? We've talked about that a lot before. And because hydronium ion is a weaker acid, that tells us that this is a stronger base or nucleophile compared to that. Since there's more HBr around as well, that means that this is the most likely thing to protonate from that HBr, generating H3O+ and Br-. So we have a lot of Br- around. Any H2O that forms is going to be protonated to hydronium ion because that's the weaker acid than HBr. So really the only nucleophile / base that we have around is Br-. And it turns out that while the conjugate base of sulfuric acid, so the HOSO3-, that's not a very good nucleophile. It turns out that Br-, Cl-, I- is a better nucleophile than it is a base. We know that it makes an even stronger acid than sulfuric acid. So it's more nucleophilic than it is basic. And because of that, it turns out that the Br- is going to act as a nucleophile and substitute for that alcohol on the carbon skeleton. So that's going to form our product. So is that Br- going to add to the front face, to the back face, to either? The answer is either, right? Same type of chemistry as SN1 that we saw in that alkyl halide chapter. The p orbital's on the top and the bottom, so it can add to the top or the bottom. So we'll just show that as a squiggle line. So that's still a wedge, but the Br added to both sides. So this technically indicates that there are two molecules present, one diastereomer that's the cis and one diastereomer that is the trans. So to finish this statement off, reacting alcohols with HX transforms alcohols into good leaving groups, which promotes, when we have HX, substitution reactions. So we have a weak nucleophile, so that's why it undergoes the unimolecular process. Now we're going to talk about what about the different types of alcohols. So this is a secondary alcohol, right? Secondary alcohols can form secondary carbocations. If you're forming a secondary carbocation, that's a stable enough carbocation to form. So this brings us to kind of the next part of our course packet. The reaction can be unimolecular or bimolecular depending on the alcohol substitution pattern. So that's what we see right here. And it turns out that tertiary alcohols, we know that they would form even more stable carbocations. So if this is going to be stable enough as the carbocation to form, tertiary is going to even happen at a faster rate. So that would undergo an SN1 type reaction. Secondary alcohols, we just talked about it, they undergo SN1 unimolecular type reactions. But primary alcohols, again, we can't, just like primary alcohols with elimination, we cannot form primary carbocations. So that means that a primary alcohol would be forced to undergo an SN2 type reaction. And again, that means that it would be the slowest. So essentially on your course packet, I have the different types of alcohols with the types of reactions they undergo, and then the rates. The tertiary would be the fastest because it's a tertiary carbocation, and the more stable the carbocation, the faster it forms. Primary, it would be the slowest because it's forced into the SN2, even though this is a really weak nucleophile. So hopefully this looks really standard, right? At this point, we've seen a lot of these steps to here. This whole process right here, before the bromide adds, is identical to the elimination reactions. The only difference is the H2SO4 leads to elimination. The HBr, so the HXs, they always lead to substitution. So essentially the reaction mechanism should look almost identical, and I really want you to focus on that. You don't have to learn anything new here. You should be able to kind of reason this out. But these HXs lead to substitution, so that's the big difference. All right.